Please join me in welcoming Dr. Amy Williams.
Excellent. Thank you so much, Jennifer, and thank you all so much for the opportunity to come out here. This is my first time out to Irvine. I am just bewildered. It is amazing. It is gorgeous, and I'm just so honored to have this opportunity to speak with you all in the room and on the live stream, and to be able to share, hopefully, my passion for space exploration. As Jennifer said, I've had the opportunity to work with both the Mars Curiosity and Perseverance rover missions. And so what I'd like to share with you today is a bit of an overview of the science that these missions are accomplishing, the incredible work that goes into it on the engineering and the science side. And one of the really powerful things for me most recently is that I joined the missions in Curiosity specifically as a PhD student at UC Davis. And I had the opportunity to really get involved in the mission in a way that carried me through my postdoc, and I was able to maintain those ties as part of my career at Towson, go Tigers. And then now I'm at the University of Florida, where I've had the opportunity to join the Perseverance rover mission. So I'm actually up in Pasadena this week participating with that team meeting. And so because we've had some new images come down, some new exciting things from our exploration of Jezero Crater, I've actually put some of that material into this presentation. So you should get some brand new, hot off the presses images and commentary from a Mars scientist. So with that, I will let you know that this is not a PowerPoint, but is a Prezi. So if you haven't experienced a Prezi before, has anyone heard of a Prezi? Okay, a couple of hands, I'll take it. So if it wants to play nice, yes, all right. So the opportunity is for us to be able to kind of zoom around, and I think this works really well when we want to talk about zooming around Mars with 2 different rover missions. So this whole talk is meant to share with you the story of the 2 most recent NASA rovers on Mars. But when I say it's a decade of Mars exploration, that's sort of going back to Curiosity landing on Mars. But really, it's more like 5 decades of Mars exploration. So it takes us all the way back to the Viking missions in '75. So these missions are actually sent to look for life on Mars. They carried several experiments. They landed, they performed those experiments, and there was maybe no life on Mars. Okay, so let's step back a little bit. What is it about the planet that we want to answer fundamental questions on, and how do we build our story up from that? So we stepped back from the look immediately for life on Mars part to let's get some more landers on Mars. Let's look at what the rocks are made of. It's a rocky planet like Earth, so the geology should have similarities, and it does. And the Pathfinder lander actually carried with it this little RC car-sized rover called Sojourner. And Sojourner was a technology demonstration to prove that you could rove a little vehicle around, send it up to rocks, and learn about their chemistry and be able to relay that back to the lander. And it was an incredible success. So beyond that, then, we knew that we could send rovers with greater and greater capabilities. So then we send the Spirit and Opportunity Mars exploration rovers to 2 different locations on Mars in order to answer the question, was there water on Mars? So that was what their search was for. And they did a fabulous job and did, in fact, show us not only was there water on Mars, there was a lot of water on Mars in its past. Lakes, rivers, deltas, and that's what you're going to hear about in part today. So beyond that, and I'm not trying to ignore my lander colleagues, Phoenix and Insight, but I want to carry on that story of more and more capable rovers, sort of our robot colleagues who are helping us to answer these fundamental questions about Mars. So we launched Curiosity in 2011, landed in 2012, and Curiosity's mission was to, instead of searching for water, search for the carbon. So we know that life on Earth, as we know it, is made up of carbon molecules. So the next step is in searching for any kind of carbon molecule, organic carbon on Mars. And that's part of what Curiosity has been and is still exploring on the Martian surface. And then finally, we come to Perseverance, so the Mars 2020 rover. And so we are taking that next step and asking, is there evidence for ancient life on Mars? So we've come in some ways full circle, but sort of head and shoulders above where we started, where we are asking that question with a really advanced suite of instruments that's coupled to Mars sample return. So we've come to understand that there are only so many instruments that you can put on a rover, and you can answer such foundational questions with them. But if you want to get at those most profound questions, really the way to do it is to bring those samples back to Earth. Right now, we do not have any samples directly from Mars. We have meteorites that have been ejected from the planet, and they've circled around the solar system for a while, landed on Earth, been altered while they've sat on Earth waiting to be found. And so they tell us an important story, but not the whole story. So now, with Perseverance collecting samples and Mars sample return, bringing them back to Earth, we'll have the opportunity to ask those profound questions about samples where we know their context, we know where they've come from, and we can finally start to link our orbital observations with those samples from the ground. So this is, in my personal opinion, one of the most extraordinary missions and architectures that we've tried to operate since Apollo. The abilities that we're going to have to better understand not just Mars, but our whole solar system from these samples is absolutely going to be revolutionary. So let's move in then to what are these missions actually doing. And so I'd like to start you out with the mission that really launched my love for Mars and Mars science, which is the Curiosity rover, or Mars Science Laboratory. So a couple of mission specs for MSL. We launched in 2011, landed in 2012. Our prime mission, so the length of time we needed to be able to operate, was 1 Mars year, which is roughly 2 Earth years. Our current status, though, is about Sol 3,444, so more than 5 years, Mars years, or almost 10 Earth years at this point. So most of my professional career has been spent thinking about what we're doing with Curiosity on Mars. And we have traversed about 17 miles, almost 28 kilometers in that time period. So I told you, one of the big things we want to do is search for the carbon on Mars. But of course, this incredible, basically roving chemistry lab has so many other capabilities. And so our major goal with this mission is to determine Martian habitability. So many people actually think that we're looking for life on Mars with Curiosity, but we are actually looking for the environments where life would want to live. So that means characterizing biological, geological, and geochemical factors, as well as better understanding planet-wide processes, including atmospheric processes. And then finally, one of the big things was characterizing surface radiation. And a lot of that actually ties back to our interest in eventually sending astronauts to Mars. We need to understand the environment they're going to experience before sending them there. And so by characterizing that surface radiation, that brings us one step closer to being able to send those astronauts. So let's step back a bit. Let me show you where we went with Curiosity. So this is a map of Mars where the colors are meant to indicate sort of elevation of the land surface. So the warm colors are higher elevation, cool colors are lower. And so Gale Crater is the destination for Curiosity. We're here on the crustal dichotomy, sort of that boundary between the southern highlands and the northern lowlands. And so let's zoom in to Gale Crater here. Okay, so we've got like a 5-kilometer wide impact crater not 5 kilometers, but 150-kilometer wide with a 5-kilometer tall mound of sediments that form this mountain that we call Aeolus Mons, but informally we've been calling it Mount Sharp. And so let's zoom in a little bit here to our landing site. So we want to land on the northern side of the crater, down in the lowlands, so that we can actually drive up onto those sediments. And one of the reasons that we want to land in this low point is that based on these images from our satellites, we can tell that there's a little, basically river that used to flow into this crater. And underneath the arrows that are drawn on here, there's actually the faint outline of what's called an alluvial fan. So a deposit that only forms when you have water flowing in from sort of a constricted river system and then dumping out into this basin. So we knew there was water here in the past. And that's one of the things we want to look for when we establish the presence of a habitable environment. So that's where we're going to head. And although we want to explore the basin and those features formed by water, we also want to go up onto the mountain because the sedimentary rocks in Aeolus Mons, in this main mountain, record actually a very dramatic shift in Mars's climate from one that had abundant water to one that was far drier. So we're basically looking to understand this major climatic shift moving towards the Mars we know today and away from that very habitable and Earth-like world that existed far back in Mars's past. So let's zoom out a little bit here. I want to talk a bit about curiosity and the mission. And so the first thing you have to do if you want to send a rover of this size to Mars is you can't use airbags, you can't use any of the systems we'd used previously. It was far too large. It's more than 1 ton vehicle. And so what we had to develop was the sky crane. So the rover uses the sky crane, which is this 8 throttle controllable rocket engines basically on a backpack on the back of the rover. And so I always love this animation because it just doesn't look like this thing is going to work. And so the rover drops down on a tether from this rocket backpack. The wheels touch the ground, and the rocket and the tether are meant to fly off and not crash on top of your rover. So because of Earth's atmospheric conditions, it's different enough from Mars that we actually were not able to test this end to end until we actually landed on Mars. So you might imagine when you finally are able to do something you couldn't test, we were extremely excited. So now we have the sky crane. Now we have the ability to deliver these really large rover payloads to Mars. So this is, of course, going to pave the way for us to send Perseverance eventually. So let's get into why we have gone to Gale Crater, to look for habitable environments. And I already told you one of the things we look for, which is water. So what else makes an environment habitable? And so the environment that I want you to start to picture is this gorgeous landscape. So this is the Yellowknife Bay region. So when we name things on Mars, we often use names for familiar geologic environments on Earth. So we've named this Yellowknife Bay. The drill hole that we're going to explore is called John Klein. And so this environment, while it looks dry and desiccated and really desolate, if you can imagine many billions of years ago, it probably looked more like this environment with ephemeral lakes that had, lifetimes in the order of tens of thousands of years, but it kept filling with water, and it would dry and fill with water and dry. And that's the kind of environment that we anticipated was in the basin of Gale Crater, actually forming what we call Gale Lake. So what are the things we look for a habitable environment? That water, of course, is vital as the universal solvent for life as we know it. We also need the key chemical ingredients for life. So that's carbon, hydrogen, oxygen, nitrogen, phosphorus, and sulfur. And finally, we need some type of energy source to feed the metabolisms of an organism. And so when we're thinking about life on Mars, we've gone to the point where we want to think about small organisms, microscopic organisms like our bacteria. So we're not looking for, large dynamic macrofauna anymore. It's really these small organisms. So what I want to do is take you down into the drill hole, the very first one that we were able to finally access the subsurface of Mars. And just remember, this is the first time that we had a drill on Mars. Before, we were just really looking at the surface or just kind of abrading the surface. Now we're getting down to 6 centimeters, which is a very short drill, but so much more than we'd ever seen before into the subsurface. And we were not disappointed because our very first peek into the subsurface at Yellowknife Bay finally revealed that the red planet Mars is only millimeters thick. It's just this very thin, oxidized layer, and you actually have this incredible diversity of rocks and basically oxidation states. That's what makes that red rust color. It's basically just iron rust on the surface. And so we finally understand that the subsurface is just as dynamic and different as we expect to see on Earth. So this just opens up opportunities for us to understand the habitability of Mars. And so if we search for these three components for a habitable environment, we do find them here in Yellowknife Bay. We find the persistence of liquid water, which was really fed evidence from us being at the end of an ancient river system that was feeding into a lake. And that chemistry of that lake, we're actually able to reconstruct that from the kinds of rocks that we see. So we can tell that the lake chemistry was really mild, it wasn't too salty, it wasn't even really an extreme environment the way we characterize them today. All of those key chemical ingredients for life were present in those rocks, and we found those energy sources for basically chemosynthetic metabolisms. So if you have minerals that have different phases or oxidation states, that can actually provide an energy source for microbes. So in our very first drill site, 7 months into this 2 Earth year-long mission, we actually characterized our first habitable environment. So great job, we fulfilled our prime mission, but there's still so much more to do and so much more to explore, and we hadn't even got to the mountain yet. So let's back all the way out from John Klein and step back to what else were we able to discover. And I'm going to try to synthesize almost 10 years of findings into basically one slide. So persistent evidence of liquid water in almost every environment that we've explored, including right at our landing site where we found these large rounded pebbles all basically glued together as a rock that we call a conglomerate. We have also found a suitable environment for microbial life, and basically all of the drill holes that we have been able to sample from so far, we found all of those chemicals required for life. The part that's really exciting to me as an organic geochemist is that we have found evidence for organic carbon preserved in these Martian rocks. Now, when I say organic carbon, it doesn't mean that we've found life, but it does mean that we've found some of the building blocks that we know go into life. We've also been exploring the presence and dynamic activity of methane in Mars's atmosphere. And this is one of the features that people keep pointing to as a potential biosignature, because on Earth, methane is only made a couple of ways, and one of those is by life. So we've been so interested to understand the sources and sinks of methane on Mars, and we are still exploring that. We've also been characterizing that radiation health risk to humans to prepare for future astronauts. And finally, we have figured out that there's a much thicker atmosphere and much more water present in Mars's past. And the video here, it's really just 4 frames put together. And it may not seem extraordinary because we are Terrans and we live on Earth, but these are clouds passing over a mountain on Mars. Just this really very human experience that you're able to translate onto a very alien world. So that is, Curiosity's discoveries in one slide. And what I want to prep you for is all of the amazing work that we still have to do, even though we are 5x past our initial prime mission. And so this is one of my most favorite images of Mount Sharp and Gale Crater. And this is showing sort of the lower reaches of Mount Sharp. All of these rock units were laid down as sediments far, far back in Mars's history. And one of the great things about these sedimentary rocks as a geologist is that you can basically interpret every single layer and tell what the environment was, how it formed, and you can basically read all of these layers as pages in a book of Mars's history. And that's why Mount Sharp is so intriguing, because as you go up in these pages, you eventually get to a point where water is not a major factor anymore. Now we're looking at a really dry and desiccated environment. And so that's what we are getting into now. So what you see here are colors put on top of a digital elevation model so that you can tell where these sediments made by water are present. So the clay-bearing unit was formed in a wetter environment, and those that were formed in a drier environment, such as the sulfate-bearing unit in yellow here. And so one of my most favorite images that's come down relatively recently is the presence of these little, they were called flowers, right? So these efflorescent salts that have grown out of that desiccated environment, and they're these delicate features, almost like a gypsum rose, that are preserved in the rock. So this is evidence of that really dry, desiccating environment. And it again indicates that major environmental transition we've been searching for 10 years to find. Now, the white line that you see here is the rover's traverse, and the little point here is meant to indicate where we are. And this actually needs to be updated because we tried to climb up onto this dark green unit called the green hue pediment, which is an aeolian or wind formed sandstone cap. And we got up onto this and found that it had this, what we called the gator-back terrain. It was this super cemented, really rugged, terrible terrain that we already have issues with our wheels, and we're trying to make the wheels last the rest of the mission. And driving on this thing was extremely challenging and could have been risky. So we've actually backtracked off of the pediment, and we've caught up with our original plan to go up that white line next to that red valley so that we can continue to explore that really dry, desiccated environment, but without the risk to our rover hardware that was present up on that pediment. So that is, my take on Curiosity and our findings over the past 10 years in a nutshell. And the really exciting thing is that for a mission that's meant to go only 1 Mars year, has gone 5 Mars years and is still going strong, the ascent of Mount Sharp continues, and there's so much more for this mission to give back to our understanding of Mars and these terrestrial worlds, the rocky inner worlds. So then let me kind of pull back here and pivot to the mission that brought me to California this week, which is Perseverance. So Perseverance, also called Mars 2020, because back in the mid-teens, we were like, yep, we're going to launch in 2020. That sounds like a great year, right? Let's just call it that. So yes, we've all had a different experience, but that name has persisted, and I think that the name Perseverance maybe means more to all of us than it did even when we first had that competition for that name, wherein these middle school students write essays about what they would like to name the rover and why, and Perseverance won out in this really extraordinary way. So a few more mission specs for Perseverance. We launched in 2020, landed in 2021. We've now driven over 12 kilometers, so we're catching up rapidly with Curiosity. We have the ability to collect samples as part of Mars sample returns. We actually have 8 rock cores on board the rover. We are meant to operate again for 1 Mars year, and we're currently at Sol 463 is what we are planning tomorrow. So the one thing I skipped on here, which is unique, is that we also have a helicopter, because everyone should have a pet robot. So our helicopter, Ingenuity, has come along with us. And we are up to 28 flights. We've flown, almost 7,000 meters. And we're actually finding that Ingenuity, which started as a tech demo, has become a really useful scout for us. So let me get back to the mission here and what we're doing. So I think there's some power in 4 topics, right? We had 4 things we explore with Curiosity, 4 big things we're exploring with Perseverance. And so this mission, again, is meant to search for evidence of extinct life in ancient environments on Mars. And so what we're doing is looking for that ancient microbial life by characterizing geologic environments where ancient life might have been present. We are looking at those environments where you might preserve evidence for that life in the form of searching in the broad field of astrobiology, which is what I study. And then we are also collecting samples for eventual return to Earth with Mars sample return. And again, if you're going to send a mission all the way to Mars, you need to have the ability to feed forward into future missions. So we also have several capabilities that are preparing for eventual human astronauts to go to Mars, including some technology demonstrations such as forming oxygen from the carbon or CO2-rich Mars atmosphere with the MOXIE instrument. So we're always sending these technologies in order to test them and demonstrate them in the real Martian environment. So let me orient you one more time to where we are. For this mission, we've gone to Jezero crater, and Jezero is really interesting because it's a much smaller crater than Gale, but it has a very distinct feature. And so if I zoom in here, it's sort of this almost fan-shaped deposit. And let's get a higher resolution image in here. So this is Jezero Delta. So as a geologist, if I see this structure, I know for a fact that this was formed by a river flowing into a lake, into a standing body of water. It's the only way you get rocks to build up in this particular way. And so this tells us that there was a somewhat long-lived lake in the crater. And these are the kinds of environments that we're interested in exploring for preserved life, because on Earth, that's where life flourishes. So even though it is this dry, desiccated environment today, we actually think in the past it looked more like this. A really robust lake with an inlet and an outlet. You have that delta deposit forming, and you also have all of those nice lake sediments that on Earth at least are a great place to look for evidence of life. So let's step back from our landing site and talk a bit about our mission. So there's a couple of things that are new with Perseverance. So we'll go through just a handful of these, even though the rovers look extremely similar in this same vehicle, almost completely same vehicle was used. Capabilities are completely different. And it actually does start with our entry, descent, and landing, or EDL capabilities. So this is sort of Sky Crane 2.0 for Perseverance, where we have a new landing technique wherein we took images of the land surface, and the computer on board was comparing that to our onboard orbital maps so that it can actually navigate the Sky Crane and find a safe place for us to land. So this is really incredible because it's going to increase our ability to land in smaller and smaller landing ellipses. If you go back to the Pathfinder or Mars exploration rovers, they had these massive landing ellipses because it was sort of like, lobbing a ball. You didn't quite know where it was going to land. But here we have these incredible capabilities. And one of the amazing things about this, $2.5 billion mission is that you can strap a bunch of GoPros onto the rover, and you can take these incredible images that have come back. And so all of these actually feed into this incredible little 3-minute video that JPL put together of what it looks like to actually land on Mars. And I animated the middle panel just to show you the Sky Crane as the rover is deployed on the tether. The bottom image is the GoPro on there looking down at the rover dropping to the surface. I think that's one of the most striking images in planetary science. The documenting of this incredible ability to land on another world. So we improved our ability to land on Mars. What are our other capabilities? So we sent, again, our little helicopter friend, Ingenuity. Ingenuity was a technology demonstration, sort of the way that the Sojourner rover was early on. So this was to test powered, controlled flight on another world for the first time. And so what we would do is, just make sure we could fly up and hover, and then come back down and settle. And then eventually we start taking longer and longer flights. I think this is just incredible, like just tracking our shadow as we're moving across the Martian surface. And so the helicopter is only meant to fly 5 times. It's flown 28 times now. So with that tech demo complete, we are now testing out Ingenuity as effectively a demonstration phase to see how future rovers and their aerial explorers can work together in order to improve our ability to survey larger areas and say, that's the rock I want to explore. Let's go over there. And then finally, sort of the reason Perseverance has gone to Jezero is to collect samples. And so now instead of drilling into the rocks, we are coring them, taking these little cores out of the rock surface. We have an abrasion bit, which is that top image, and then the coring bit at the bottom. And so it's just a cylindrical drill that cuts out samples from rock interiors. Each sample is collected directly into a a clean sample tube. And so you're actually seeing part of that in the drill bit, and the rock inside of it is going to get fed into one of these sample tubes. And so each core is only going to be about 1/2 inch in diameter and not even 2.5 inches long. So some of the most precious little tiny rock samples that are really going to revolutionize what we know about Mars, when the water was flowing, what the geochemistry of these rocks really is. And one of the really great things we can do is take images with what we call our cache cam. So we're looking at our rock cache and seeing with a Z-stack kind of how far down the rock is. We look at the volume so we can figure out how much material we sampled, and then we cap it so that it is hermetically sealed so that it is safe from any alteration as we bring it back to Earth. So those are some of the firsts with Perseverance. And so what I'd like to do in sort of the final exploration of Jezero that we're in now is talk about what we've seen over the past 1.5 years on Earth years. So initially we landed in the crater floor. It was one of the safe places to land according to our new entry landing, descent and landing system. So we landed in the Octavia E. Butler landing site. And let's zoom into this a bit more. And so we landed sort of on the edge of these two distinct morphologic units. We wanted to understand, what are we on? You know, we came to this place, we know there was water, it's got to be a lake bed, right? So let's go look for all of these sedimentary rocks. So we start driving around the white line here, sort of around this feature, down to a place where we can actually get down into that lower feature that we call Seta. And as we're driving around, we're seeing these layered rocks. We're seeing these like low layered paver rocks, and you know, something's weird about these. So like it's not quite what we were expecting. What's going on in this crater floor? And for those of you that have any geologic background at all, which you may see in this final image when we got down into Seta, these rocks, does anyone know minerals? Maybe a little bit. So these blobs that you see in the rock here, these are the mineral olivine. And these are actually olivine cumulates. The only way you form that is in a basically volcanic or igneous system. So in this lake bed that we were expecting to land on, we actually landed on a lot of volcanic rock. So it turns out that there is all of this igneous rock in the center of Seta, that Mars unit on the side is all lava flows. So now we have a very different environment than we were anticipating, but we suddenly have a new opportunity because we have the ability, with the samples that we've collected here, to date a specific age for all of these rocks on the crater floor. And we can tell basically how old those are relative to the delta that's flown down on top of it. So this is actually a great opportunity. We've collected from 4 different sites along that traverse around Seta. And for each of these, you'll see kind of 3 images. The images on the left are an abrasion from that abrasion bit where we can see the surface and we can do a lot of kind of contact science on that abraded fresh surface. And then these other images are all of the cores before they were sealed up. So we have all of these incredible samples from the crater floor, and of course, the igneous petrologists on the mission are just, you know, happy as clams that we've got all of these incredible rocks. Those of us who are really on the sedimentary side are very excited to get to the delta, the whole, you know, one of the big reasons that we came to Jezero. And so, again, going to Jezero and heading towards the delta, the reason we're doing this is because river deltas are habitable environments. So we would hope to see evidence for life. If life had been present, this is a great place for it to be preserved and to have lasted billions of years in that preserved state for us to be able to sample it. One of the things that helps preserve that evidence for life, and a lot of that goes back to the search for like microfossils or organic carbon that's very definitive of life. And there's specific kinds of clays, in this case, smectite clays, that are found in the delta and are also ideal for preserving organic matter. And so what we did was when we completed the Crater Floor campaign, we made a beeline around Seta, because we couldn't really drive on it, over to the Delta Front. And as we back out, you can kind of see where we landed at that Delta Front location. So these are kind of brand new things that have come down from the rover just in the past few weeks up until like past couple of days, really. So I've zoomed in on an orbital image of the Delta Front. So sort of all of this loby stuff up at the top of the screen is where that river was flowing into the lake and all that sediment was depositing out into the structure. And so some of the really incredible images that we finally got from the ground include this incredible feature we've called Temple Hill. And it's just this really perfect little cone shape. And so we think that it is a remnant of the Delta Front that's being eroded back, sort of like sea stacks on the coast. And in the mid-ground, you can actually see the front of the delta in that particular location, and then the far, far background there is actually the crater rim. So you have multiple levels of really incredible geology that you're able to interrogate just with these high-resolution cameras on board. So looking down at this like weird sort of knob feature here, this is Kodiak. This is one of the most striking images to me. I've got this big picture up in my office of this because it is so distinct to a geologist to look at these features and say, well, that was formed by a river flowing into a lake. This is definitively a delta. And so the structures that you would see, these right here and those right there, are indicative of that river kind of prograding out into the lake and forming these structures. And this image is spectrally stretched so that you can see the difference between those igneous crater floor rocks and the sedimentary rocks that make up the delta. And so we finally got up to the delta front. We want to interrogate, we've been exploring these igneous rocks for over a year. And so we finally reach our first sedimentary rocks of this mission at this place called Cape Nookshack. And this little environment right here is called Enchanted Lake. And we were very hopeful when we were naming these, these units, but we lucked out in that, yes, these are sedimentary rocks. And so what we want to do is collect the best possible samples for eventual return to Earth. So what we did was actually drive around that cape and up to that environment there, which we call Hawksbill Gap. And so this is this really nice suite of rocks that are going to tell us about that delta prograding out into the lake. And we want to collect samples that are representative of different sort of energy regimes, right? So faster moving water can move bigger grains, slow water will only be able to move very fine grains. And you can learn a lot about an environment by selecting samples from those different facies. And so that's what we're doing. In this image, oh, you know what? I think it came down 2 days ago. And this, yeah, right. So I promise, I told you we would see some new things today. This is a place that we're calling Hogwallow Flats. We have really fun names. And, we don't know what it is yet. And that is the absolute joy of exploration. It can be on another world. It can be in your backyard. But that's the joy of just, what is this? Let's find out. And that's part of what makes my day job such an absolute joy as well. So that's Perseverance. That's our mission. There is, of course, the follow-on mission to this, which is Mars Sample Return. And, this talk is about the last decade of discoveries from Mars, but truly Mars Sample Return is the next decade, and I would say decades of Mars exploration and discoveries, because again, getting these samples back and ground truthing things that we've only been able to interpret from, very robust instrument suites, but still limited, right? The number of instruments you can send on these missions is limited. And so bringing these samples back and sharing them with the best scientists and labs around the world is the way for us to address these most extraordinary questions that impact not just our understanding of other worlds and of Mars, but actually our understanding of our own planet and how Earth and Mars, which started out so similarly, have diverged in so many fundamental ways. So I think that this is the way for us to start to understand not just Mars, but ourselves and our planet more fully. And so with that, let me just step back and, as an astrobiologist, I'm passionate about the search for life beyond Earth, but also better understanding the life here on Earth. So the search for life beyond Earth really leads me to finish with my favorite quote from Carl Sagan, that the universe is a pretty big place, and if it's just us, it seems like an awful waste of space. Thank you all so much for coming out tonight.